And today, by the end, we want to finish our environmental setup. We are going to be using HackerRank and Leetcode for practicing purposes. And we are going to be uploading our codes into GitHub. Like we want to create our repository in GitHub that we can point to recruiters in the future if they want to take a look. So if we start from the early days uploading everything there, that's going to be awesome. So I highly recommend having a good structure. You can talk with your mentees or your assistants. They can tell you what kind of structure would be nice to have there. And moving forward, once we solve these questions and gets accepted from the platforms, we are going to be uploading them to GitHub. All right, so let's get started. What is an algorithm? Like in general, an algorithm. Oh, thank you. Okay, yes. In general, an algorithm is a step-by-step procedure for solving a problem. It doesn't really have to be a computer science problem. For example, cleaning this lab can be a problem, and step-by-step procedure can be, okay, first go around, collect all the bottles of waters, put them in a bag, and leave them the lab. This can be an algorithm. And in computer science, the definition is more like well-defined computational procedure that takes a set of values as input and produces another set of values as output. So let's think about that. Can anybody give an example for an algorithm? You get an input, you produce an output. They don't have to have same number of inputs and outputs, but they can have two. It can get one number and it can produce one number, for example. Can anybody think of an algorithm? Yes?
Making tea.
Making tea. Making tea. Like in computer science concept, let's say.
Binary search.
Like what is input, what is output? Let's try to stick with this definition here.
Searching for a person in your contact list.
Searching for a person in your contact list. What is our input? Probably name of the person. And the output we want to return is the number of the person. It can be that. Or we can even think of very simple operations like summation. What is summation in essence? How many numbers we get for summation? In the most basic form, we get two numbers, right? And the returned output, the desired output, is the summation of them. So these are all examples of algorithms. So some other examples, let's take a look. Fibonacci. Are we familiar with Fibonacci series? Have you ever heard of Fibonacci? Like basically, fib n is equal to fib n minus 1 plus fib n minus 2. But obviously we need to have a base case, right? This cannot go until negative infinity. So the base case for Fibonacci is f1 and f2 are equal to 1. So let's take a quick look here. We say f1 is equal to 1 and f2 is equal to 1. And the definition we have is fn is equal to fn minus 1 plus fn minus 2. So if we want to calculate f3, which values are we going to refer to? f2 and f1, right? And from our base case, we know that these two guys are 1. So f3 is going to be equal to 2. Likewise, if we want to calculate f4, by the definition here, we know that it's going to be f3 plus f2. And from here we know f2 is 1, and from here we know that f3 is 2. So f4 is going to be 3. So did we get what Fibonacci series is? And if we say we are given n and we want to calculate fib n, then the way we are going to produce this result is going to be an algorithm. We already talked about summation. What is sorting? Is there anyone who is familiar with sorting operation?
It's a way of rearranging items or objects in some meaningful order.
Like given some, I guess, like comparison function, right? So let's say we are given integers. If we want to sort them, like the most basic two ways of sorting them are in increasing order or in decreasing order, right? Let's say if the numbers are 3, 4, 2, 1, minus 3. And if you want to sort them in increasing order, then the desired output would be minus 3, 1, 2, 3, 4. Shortest path. Let's say we are given the map of Ethiopia with all the roads. And let's say there are no riots or anything, so all the roads are open. And we know the distances. And we want to go from here to Harar. So which path we want to take so that it's going to take the least amount of time to get there. So this is the problem of shortest path. And you can replace Addis and Harar with any other two cities. Again, this is going to be the generic shortest path problem. So how about compression? Like we are all familiar with many different types of files in our computers, right? And obviously we don't want them to get a lot of space because space is limited. And to be able to represent the same amount of data or a little bit of loss, there are many different compression algorithms that we can make use of. So with the help of them, we can represent the same data or somewhat the same data with very little bit of loss in a very smaller, in way smaller space. So these are all examples of algorithms. So now let's take a look at types. And moving forward, we are going to be doing everything in Python. But since today we also had the introduction, I didn't have time to renew these slides. Sorry about that. And we are going to cover C++ types. But I'm pretty sure Python has like somewhat, similar types, right? So let's take a look. The first type we are going to cover is a character. So in C++, the characters are coded with ASCII values. And their values are in between either like minus 127 to 127, or you can think of 0 to 255. Where does this 255 number comes from? So from 0 to 255, how many different values we have? 256, right? Is there something special about this number? What is this number equal to? 2 to the power of 8, right? And can someone tell me like how much of a space we are gonna need for a character in C++ then?
1 byte.
1 byte, which is 8 bits, right? Like this 8 is actually representing that. We have an 8 bit of a space, and each bit can take values 0 or 1. And as a result, we can represent 256 different values in this space of 1 byte. And that's how we represent simple characters in C++. And the second type we are going to care is unsigned char. So in C++, the sign is represented by the first bit, or we can say the leftmost bit. So if this bit is 0, then it means the sign is negative or positive? Positive. And if it is 1, it means the sign is negative. So if we are using 1 bit to represent the sign, how many bits do we have left? 7 bits, right? Therefore, we can represent values up to 128 and starting from minus 128. So why do we have minus 127 and 127 instead of 128 and minus 128? Indeed, there's a typo. So the negative one should be minus 128. Why is that? Is there a number without a sign? 0, right? So we need to have a place for 0 as well. If we don't have any place for 0, then we can only represent negative and positive numbers. To be able to represent 0, that's why we are sacrificing one of the positive numbers, and it can go up to 127. So now let's take a look at integer. Indeed, it's going to be completely the same logic, guys. So instead of having 8 bytes, in integer we have 32 bytes. That's why these numbers are going up. Instead of having 127 as 128 as upper bound here, 127 as upper bound, we have this number a little over 2 billion. And again, 0 is on the positive side. That's why the negative limit is not equal to the positive limit, because 0 is eating 1 space from the positive side. And in an unsigned integer, again, we have 32 bits, but this time we are not losing the first bit for the sign. That's why our capacity goes up to 4 billion something on the positive end. And there is also a type called short int. The logic is again very similar. This time we have 2 bytes instead of 4 bytes. That's why the capacity is limited with 32,000 something. It is 2 to the power of 16. Because in 2 bytes we have 16 bits, right? And unsigned shortened, I think you guys already got the logic here. So like float and double are the interesting ones. In order to represent decimal numbers, we have 2 types in C++, float and double. Like nowadays, float is not used that much anymore because it's not that precise. So double is a better format to represent the decimal numbers. And depending on your environment, some of these sizes may change. Like long int, for some compilers, it is 8 bytes. For some compilers, it's 4. That's why you should check by yourself to see what is going to be the exact size. I'm not sure if there is such thing for Python. Probably not, right? Okay. Cool. Any questions up to this point about types? So in your favorite programming language, please get to know what types are available, how much space they are using, because once we do time-space complexity analysis, that number is going to play a big role. Because there can be some algorithms that are not going to be working because of the space requirement you have. So with normal integers, it's such an easy operation. How about making summation with gigantic numbers? Like with numbers that can have up to million digits, let's say. How would you approach to that problem? Anybody wants to tackle? Interestingly, this problem is going to take us back to the primary school days. How were we solving summation problem in the early days, guys? When you were 7 and you were given 2 numbers, how were you doing the summation operation? Is there anyone who wants to show us on the whiteboard? Can we get a volunteer? And Isiak is not here, so maybe we need a new random teammate generator. Come on, we are gonna help. Nobody wants to come to the whiteboard. Hands. Burak. Anybody from group 2? You. Yes, please. Come. Don't worry, we are not gonna eat you. So let's make some space here. So we are given 2 numbers. And then we want to sum them.
So we start from the last.
There is a plus sign.
Okay.
Thank you.
So we start from the last digits. For the first number, the last digit is 2, and for the second number, the last digit is 3. So we add 2 and 3. Is 5. Then we go from the right side to the left side. So 7 and 1 is 8, and this is 9. And this is 13, which is 3, and we have 1, and this is 10. So this is, I guess, the basic summation operation in the.
That's how we would do it in primary school, right?
Yeah.
So now let's think about that. Now we are given, let's say, up to 1 million digits of 2 numbers. And in our favorite programming language, we want to implement summation operation. Can we get any inspiration from this algorithm?
The thing is that if we try to do this with the integers, it's an overflow, obviously. So I think we can convert to the strings, probably, most probably. because strings may have, you know, a lot of more space than the integers. Then we could try comparing the two strings, one by one, as a friend showed here. Like we just need to simulate this operation in the computer, actually.
And depending on your favorite programming language, you may not have to do that, right? Is Python supporting summation of big integers by default? Okay, but let's say we are going back to the early days, and we are in 2005. There is no Python yet. The idea though, right? Cool. So this is gonna be our first homework for today. Now let's take a look at another problem. So this time, instead of summing these two numbers, we are trying to multiply these two numbers. But this time they are not gonna be that gigantic. If they are million by million, it can take a little too much time. So how about making them numbers with 1000 digits? How can we approach? Okay, I guess to make things a little bit more colorful. Oh, where is the eraser? Ah, thank you. And let's make your job a little easier. Should we go back to the primary school days again? Who wants to do it this time? Who is confident in their arithmetic skills? Okay, let's see. Yes.
We're going to multiply 3 by 2, giving us 6. Do I have to do?
Yes.
Can I explain?
Yes, please. Could you please explain us as well the operation? Yeah.
And then I'm going to multiply 3 by 7. That's 21, so I'll have a carry. I'll write 1 and I'll write my tens place 2 as my carry. And I'll multiply 3 by 3, that's 9, 11, carry 1, and 12 and 13. I'm just going to write this whole number because multiplying by 1 gives the same number. And multiplying by 6, 6 by 2 is 12, carry 1, 6 by 7 is 42 I think, 3 carry 4, multiplying 6 by 3, 18 and 22, carry 2, and 6 by 4 is 24, right?
Yeah.
Yeah, and 26. No wait, oh yeah. And I'm just going to add these 3 numbers. By simulating. 6, 3, 0, 0, 1 and 6 and 8 and 6 and 2 I think, if I'm correct. This is 8.
Okay, we believe you. Thank you very much. And so now let's also think of how we would do this job with a computer.
I think the simulation would still work with multiplication with minor changes to the particulars of the program. We probably want to maintain our carries. We want to, we don't want to forget them, and then the addition is, again, it's another, so probably we'll divide our algorithm into 2, one to add the first algorithm and then one to multiply.
And indeed here we also see a very important principle of software engineering. Like we can make use of the functions that we have defined in other places for solving more complex problems. So if we first write an algorithm, like write a function for doing the summation operation, indeed it can be super handy when it comes to writing a function for calculation, writing a function for multiplication, right? So here, let's say after we calculate these these middle results, like by shifting this number, adding this 0 here, I can call summation for these two. And then for this one, shifting this to the left by 2, calling the summation on top of this, again, is going to help me to find the real multiplication result. So this is going to be our second homework. Multiplication of two big numbers. And then, like at this point, if we had the electricity, we were going to go ahead and create our accounts for HackerRank and Leetcode if you hadn't done already. And then we were going to tackle these two problems from HackerRank, and then these three problems from Leetcode. And finally, we are going to finish our lectures with the quote of the day. And today's quote comes from Mahatma Gandhi. And he says, "Live as if you were to die tomorrow. Learn as if you were to live forever." So if you are going to die tomorrow, I'm not sure if you are going to be in this class, so please get out now. And yes, we need to keep in mind that learning is the most powerful thing. So in the last year, maybe not last year, but in the last 6 months, I have been reading a lot of books about leadership. And the one thing that was in common on many different resources that I have checked out, they all say that constant learning is a must, and your learning capacity is directly proportional with your leadership ability. So many of you guys mentioned that you want to be entrepreneurs, you want to have your own company in the future. So it means you guys are going to be leaders of the future. So in that case, we should take this advice seriously and try to invest in increasing our learning capacity. Thank you very much, everyone. This was very enjoyable, and welcome to the team again.